Welcome to our probability unit. Today we're going to be talking about probability and the likelihood of events. So this is very vocabulary heavy. Some of it's common sense. Hopefully you'll enjoy this unit. It's kind of fun. An experiment is an activity involving chance when we're talking probability. Each repetition or observation of an experiment is called a trial, and each possible result is an outcome. The sample space of an experiment is the set of all possible outcomes. So if we're rolling a number cube, a standard number cube is just a die. Okay, the sample space, we could write it in set notation. The possible outcomes, you can roll a 1, you could roll a 2, you could roll a 3, you can roll a 4, you can roll a 5, and you can roll a 6. If you're tossing a coin, you can get a heads, or you could get a tails. If you're spinning that game spinner, you could get red, you could get blue, you could get green, or you could get yellow. Those are the sample spaces for those particular events. An event is an outcome or a set of outcomes of an experiment. Probability is the measure of how likely an event is to occur. Probabilities are written as a fraction or as a decimal from 0 to 1 or as a percent from 0 to 100. The closer the probability is to 1 or 100%, the more likely it is to occur. The closer the probability is to 0 or 0%, the less likely it is to occur. So this little chart gives you an idea of what I'm talking about. So impossible is a zero event. The probability is 0. It is never, ever, ever going to happen. So like if you have one dice and what's the probability that you're going to roll a 12? It's impossible. There's not a 12 on that dice. Okay. As likely to as not, that's your 50-50 chance. So events with a 50-50 chance are equally likely to happen. So like on rolling a dice, the chance of rolling an even number, half of the numbers are even, so you'd have to have 50-50 chance. Certain 100% chance of happening. If you roll a dice, you're going to get a number that's 1, 2, 3, 4, 5, or 6. Okay. So as likely to occur as not, that's a 50%. Less likely to occur is going to be like from 1 to 49%. More likely to occur would be like 51 to 99%. Impossible is going to be 0%. Certain would be 100%. If something is extremely unlikely, doesn't mean that it is impossible. No. Winning the lottery. Being struck by lightning. Those sorts of things. Okay. If something is extremely likely, doesn't mean that it is certain. Again, no. How about having school tomorrow? Okay. Classify each event as certain, likely, equally as likely as not, unlikely, or impossible. Flipping heads on a coin. Well, that's equal, right? 50-50. Rolling a 6 on a standard number cube. Unlikely. Right? You only have a 1 in 6 chance. Rolling a factor of 24 on a standard number cube. So factors of 24, that means what? If you divide, what's 24 divisible by on a number cube? So 1, 2, 3, 4, not 5, and 6. So all those numbers, so pretty likely. Spinning a prime number on a spinner labeled from 1 to 10. Well, prime numbers from 1 to 10 would be 2, 3, 5, and 7. That's almost half, but not quite, so unlikely. Rolling an integer on a standard number cube. Well, that's certain. There's only integers on a standard number cube. Rolling a multiple of 7. So 7, 14, 21, so on. That's impossible. Because only 1 through 6 are available. Okay, so again, the set of all possible outcomes of an experiment is called the sample space. And a coin is tossed and a number cube is rolled. What are the possible outcomes? How large is that sample space? There are two ways to show the sample space for an experiment. You can make a list or make a tree diagram. Okay, so the possible outcomes for tossing a coin are heads, we're going to use capital H, or tails. Okay, the possible outcomes for rolling a number cube are 1, 2, 3, 4, 5, and 6. So if we make a list, the sample space would be like heads and a 1, heads and a 2, heads and a 3, heads and then a 4, heads and a 5, heads and a 6, or tails and a 1, tails and a 2, tails and a 3, tails and a 4, tails and a 5, tails and a 6. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 possible combinations you could do in that experiment. Okay, the other thing you can do is make a tree diagram. So our possibility is heads 1 through 6. So H2, H3, H4, H5, H6, T2, T3, T4, T5, T6. Oh, so again, you can see these look like trees. Sometimes you would do like heads and then 1 through 6 that way, and tails 1 through 6 that way. And they kind of look more like trees when drawn vertically, but they can be drawn horizontally as well. Saves a little space on the paper. Okay, and again, this would give us our 12 outcomes. But if you're doing lots of different things, what if it was a 12-sided dice? What if you were doing a 6-sided dice and then a 12-sided dice? How many outcomes would you have then? And listing them would get really long, okay? So we also have something called the fundamental counting principle. The fundamental counting principle says if you have A ways of doing event 1, B ways of doing event 2, and C ways of doing event 3, and so on and so forth, you can find the total number of outcomes by multiplying A, B, and C. So we had 2 ways for heads, 6 ways on our dice. That would give us 12 ways, right? We had 2 ways of doing a coin. We had 6 ways of rolling the dice that gave us our 12 possible outcomes. So like I said, if we had that 6-sided dice and then the 12-sided dice, we'd just do 6 times 12. Okay? So a class is choosing a president and a vice president. There are 3 students running for president, Maria, Anna, and Linda. And there are 3 students running for vice president, Jim, John, and Bob. The tree diagram shows the possible outcomes. Okay, so for president, we can have Maria, Anna, or Linda. For vice president, we can have that combination. Okay, so how many outcomes are there? So our outcomes, we just count. 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 possible outcomes. How many outcomes have Jim or Bob being chosen? Okay, so Jim or Bob, Jim or Bob, Jim or Bob. So 6 of them. Now, how many outcomes chosen have both Maria and John being chosen? Okay, so Maria and John there. Do we have any others that include Maria and John? No. Okay. A standard number cube will be rolled once. The number rolled will be recorded as the outcome. Give the sample space describing all possible outcomes. Okay. So we can get a 1, we can get a 2, we can get a 3, a 4, a 5, or a 6. Now, give all outcomes for the event of rolling a number greater than 3. So those possible would be 4, 5, and 6. A coin will be tossed twice. Each toss will be recorded as heads or tails. Give a sample space describing all possible outcomes. Then give all of the outcomes for the event that the second toss is tails. Okay, so if we do heads, it could be followed by a heads. We could get heads followed by a tails. And then we can get a tails followed by a heads, and we could get a tails followed by a tails. And then it says second toss is a tails. So we could get heads and then tails, or we could get tails and tails. Peaceful Travel Agency offers vacation packages. Each vacation package includes a city and an airline. The agency offers 2 cities and 4 airlines. How many different vacation packages do they offer? Well, our first possibility is 2. Our second possibility is 4. So that means there's 8 total packages. Okay, that's using that fundamental counting principle. All right, a toy company is going to issue some ID codes for its employees. Each code will have 1 letter followed by 5 digits. The digits 2 and 6 cannot be used. So there are 26 letters and then digits that can be used. Assuming the digits can be repeated, how many employee codes can be generated? Okay, so how many digits are possible? So how many numbers? Well, a single digit is 0 through 9, and we can't use 2 and 6. So the digits we can use are 1, 2, no, we can't use 2. 0, 1, we can't use 2, 3, 4, 5, can't use 6, 7, 8, and 9. So that means there are 8 possible digits. Okay, and then it starts with a letter. So we have our letter, right? And there's 26 possible letters. And then how many followed by 5? 1, 2, 3, 4, 5 numbers. And each time we have 8 numbers to choose from. So we're going to take 26 times 8 times 8 times 8 times 8 times 8. That gives us 851,968 possible ID codes. That's a lot of codes.